Hello and welcome back to Calculus 1 Exam 3 review. So Exam 3 on Chapter 4, 10 problems. So it's like 17 altogether. Right? Exam 3, Chapter 4, 10 problems. So what do we have? A problem on min-max, that's 4.1. Should be able to differentiate set equal to 0, find critical number, and then check if that's min or a max for a function. A problem on first derivative test, which will have the full work in terms of find the derivative, set it equal to 0 for critical points, do the partition with critical points and asymptotes if you have any, pick test values, and then find interval of increase decrease. As freebie, you get min max as well. Second derivative test is going to be completely separate problem. You have to take the first derivative, then you have to take a second derivative, set it equal to 0, and then do the same procedure. Partition using inflection points and asymptotes, pick test points, plug in a second derivative, and then look for concavity, concave up, concave down. We're talking about intervals. Your final answers have to be intervals. For first derivative test, it should say interval of increase, right? And then you will have maybe union, or not. You will have intervals from x1 to x2. Same for second derivative test. You will have intervals of this. Graphing. Everything is given to you. X-intercepts, vertical asymptotes, horizontal asymptotes if any, slant asymptote if any. So all of the info that you need for graphing, which you would obtain from these things and other asymptotes and stuff, algebra, all of that is given. You are supposed to look at the information provided and draw a graph. You had a very similar question on exam 1 with limits. I gave you 5 things, and then you were supposed to draw the graph looking at those 5 things. Linearization, fancy word for tangent line. Use linearization to compute ln3, ln5, ln10, tangent of 7 degrees. So use linearization to either compute the value or, to get the tangent line. We know linearization does both. Remember that I told you tangent line, exam 2, exam 3, and the final. You cannot escape tangent line. That is the most important problem of Calculus 1. Mean value theorem 4.2. Average equals the instantaneous. You got to know the formula and conditions. Because if the function is not continuous, theorem doesn't hold. Right? So mean value theorem doesn't hold if the function is not continuous. If it's not differentiable, doesn't work again because one part of the formula is f prime. Well, if it's not differentiable, how are you going to do f prime? See that? So you need to know conditions. If the function is differentiable, if the function is continuous, then on the interval a to b, we have, and then you have the formula f prime equals f of b minus f of a divided by b minus a. So instantaneous equals the average. We did few word problems within that one, but you also have those problems where you're just computing for C. I called it, I think, mathematical gymnastics, right? And then the word problems, optimization and differentials. Optimization word problems, I believe that was 4.4 or something like that. Optimization word problems, we did quite a few. Some of those were the fence, right, for the farmer. We did the business application with the pipe. Remember the pipe for? So we did all of that stuff, and it was all of that stuff is possible. So farmer, fence, and business, and other geometry with triangles. So we did a lot of examples, and we can do some tonight if you have anything in mind, for sure. Differentials. The key wording, and I've seen this throughout the years. People say, "Well, I don't really know which one because." If you give us the mean value theorem word problem and then the optimization word problem and differentials, so which one is which? Well, first of all, you recognize optimization because they're looking for maximum area, minimum surface area, maximum volume, minimum surface area, maximum or minimum distance, right? The words minimum and maximum are present, and that's the equation that is objective equation. We'll have min or max. So that's clear. Where the differential problems are asking to approximate the change. It clearly says what is the change or something like that. So these are the parts where you differentiate which problem is differential, which problem is optimization, and the mean value theorem doesn't have any of those keywords. Mean value problem was the one that we did with the police. Between two checkpoints, and then there was also runner. That was the same pretty much deal. So these problems are very distinct. So that's the exam, right? 10 questions, and you guys answer, and then obviously draw something nice in the back of the exam. Questions, concerns? Yes?
For the first period test, I don't remember what it was. How do you for the asymptote?
Well, if the asymptote is present in the function, the asymptote will be present at the same place as the derivative of that function.
Okay.
So if your original problem had the asymptote at x equals 2, it will always be x equals 2 throughout the derivatives taken. So your... let's say you have x equals to 2 as asymptote, then that becomes also partition. So you might be having the domain from negative infinity to positive infinity, and then maybe you have critical points at 0 and 10. You will be partitioning at 0, 2, and 10. Okay. Because 0 and 10 are critical points, and 2 was an asymptote. So you will have 4 parts.
You know how you find between solid inflection points?
Yeah.
Say we have something like a cube root function, right? When you go from negative infinity to infinity, since it's always decreasing, or would that be negative infinity to the inflection point to infinity?
Depends on what. If you are talking about decrease, then it's decreasing all the time. If you're talking about concavity, it's not. So concavity will have 2. All right, so the question is, if I have a function y equals inverse tangent of x, which has these horizontal asymptotes at negative pi over 2 and positive pi over 2. And you draw inverse tangent function. The question is the difference So clearly, no min, no max in this function. That is immediately clear because the derivative, y prime, is 1 over 1 plus x squared. And when you set that equal to 0 and cross multiply, you get 1 equal to 0, right? So no critical points means no min, no max. So no CP implies no min, no max. And then You don't have any asymptotes either for partitioning. So everything is one partition. And you are allowed to pick any value to plug into this derivative. Any value, because the whole thing is one partition. So what do you pick? Well, test point 0 is easiest, right? Pick 0. So 1 over 1 is 1. See, that's bigger than 1, so it's always increasing. You see that the function is always increasing. So all one partition from negative infinity to positive infinity. And then you pick 0 as a test point because it's cheap. And when you plug that, f prime of 0, 1 over 1 plus 0 squared is 1, bigger than 0, increase. We get that the function is increasing on the entire domain, which we can see because I gave you the graph. Inverse tangent graph is something that you should have memorized all the time because it's going to come up many times. And as you are looking at this graph, it's clearly increasing everywhere. Now, second derivative test. Well, for the second derivative test, I see that I should have some motion here because I see this part of the graph as concave up, right? The curvature would fit, right, for something like that. And the other part is kind of opening downwards. So this suggests that there is an inflection point at 0, changing concavity, and I have concave up and concave down by looking at the graph. But we can all prove that using our second derivative test. So as you can see, one partition for the whole problem for increase-decrease, so the first derivative test, but there will be at least 2 partitions for the second derivative. Well, let's take the derivative, see what happens. The fastest way to take this derivative obviously would be if you use the chain rule, because this is that, right? Bring it up. Don't use the quotient rule. Like why swing a sledgehammer if you can just use the regular small framing hammer? So y double prime is going to be -1 times 1 plus x squared to the -2 times the derivative of the inside, which is 2x, is a chain rule. So my second derivative here, should have left this problem for the test, it's awesome. No coughing, plus a square, there we go. So now, that's your second derivative. When you set this equal to 0, 0 times the denominator, it's going to kill it. But you have -2x equals 0. X equals 0 for the inflection point, as I have foreseen. I know the graph, right? So now we know there is inflection point at 0. So 0, 0 inflection point. And partition now, which is negative infinity to positive infinity. Partition has a 0 right there as a partition. So now we get to pick -1 and +1 test points. So f double prime computed at -1 is going to give me -2 times -1 over positive number. I don't even care what it is. I have denominator squared. And if denominator is squared, it's going to give me a positive value. So now negative times negative is a positive. Positive divided by a positive is positive, which is bigger than 0. So concave up. Hey, we know it's concave up. Look at it. Concave up. Right? Wouldn't you agree? Concave up? Yeah, concave up, right? The second one better be concave down. And it is. because second derivative computed at 1 is negative 2 times 1 divided by a positive again. Negative divided by a positive is equal to a negative less than 0 concave down. Note that I didn't compute anything. Can you go and plug in negative 1 for each x, use a calculator to come up with a value at the end? Yes. All we care for both first and second derivative test, all we care is whether the number is above or below 0. If the number is above 0, function is either increasing or concave up. If the number is below 0, function is concave down or is decreasing, right? Depending on which one you're using. Both tests are identical. Just the first derivative test uses the first derivative and the second one uses the second derivative, right? All the calculations are the same. All of the, right, at the end you get the partition test points and then you plug test points to your derivative. So it's very structured. And I'm going to separate these. I'm not going to give one problem, right? I mean, I could say graph the function and give you the function and check all of these, like half of the chapter in one question. Because, right, you min or max, your asymptotes, your first derivative test, the second derivative test, graphing, right, all of that. Remember the shopping list of all the things you need to figure out before you graph, right? No problem, 50 points, easy, right? But then what happens if you mess up on a first derivative, right? You forget a minus sign. So I learned to separate these into, a whole bunch of problems, and then you put the pieces of the puzzle together. One thing that the list is missing is L'Hopital's rule, and I don't know why. So there will be L'Hopital's rule on the thing. So now I have to go back to the list, and here in blood add L'Hopital's rule.
And the antiderivative stuff, right? No?
Yes. Wow, that's missing too. Oh. There we go, much better, thank you. Antiderivatives are the one with the plus C from 4.9. All right, so what do we have there? For L'Hopital's rule, we know it's for 0 over 0 or infinity over infinity. What are the other cases that we might run into? 0 times infinity, which uses what? F is equal to 1 over f trick. Infinity minus infinity, which uses factoring. Then f equals 1 over f. And then we have 1 to infinity with its friends, 0 to 0, and so on. And that will use log ln both sides, and then follow whatever math brings. So L'Hopital's rule works only for these. Everything else that you do are the tricks, the algebra manipulations to go to this form, and then you use L'Hopital's rule. Yeah. Example of a log. Which one? Yeah, but which one? What do you mean you don't know? You asked for it. You did?
Yeah, x to the h, semicolon, e to the 0.04. That's where you compare the two. Use the limit method to determine which of the two functions grows faster.
That's not L'Hopital's rule. But keep that. That's a good question. We'll do that next.
I thought you get that into the same form if you use log form.
No, you don't have to.
I have no idea.
Maybe, I don't know. Any? Okay, how about, so you see this, try limit x raised to the 1 over ln x as x goes to 0. This is a really cool question, 0 plus, right? This is a really cool question. Okay, let's take a look at this together. So y equals, leave some space, limit x goes to 0 plus x 1 over ln x, and we ln both sides. On the left hand side we have ln y is equal to, now we swap the spots, limit goes first, 1 over ln x, and then we have ln x. Exactly, they just cancel out, right? So that's equal to 1. And we have ln y is equal to 1, e both sides. Y equals e. And that's the limit. So limit x goes to 0 plus of x 1 over ln x is equal to e. Ta-da! Done. We good? Good.
Now it's fine. It's the same thing. I just flip it around so it's like 1 over x squared.
All right. Good. Anything else? You had that problem.
It was in 4.7 and third.
Yeah, that's at the end of, we're talking about the rate of increase of functions. So what were the two functions?
X to the 8 and e to the 0.04.
Great. Growth rate. So the growth rate of functions would go ln of x is growing slower than x to some power p. It grows slower than x to the p ln x. Grows slower than exponential. This list will be expanded on. Grows lower than x to the x. We can put more stuff in here, but generally this is it. So now this means that the limit x goes to infinity of x to the 8 over e to the 0.04x is, well, you have slow over fast. And when you have slow over fast, because this is rising quickly, the other one is rising slowly, and you have to actually go far in calculations to see this. You get slow divided by fast is, what is it? 0. Good, 0. Slow over fast would be 0. Because these numbers are going to become huge, these numbers are going to go at much slower rate, so you will be dividing it. But we can also say limit x goes to infinity of e 0.04x divided by x to the 8. In this case, it would be positive infinity. Please note that if you are to take L'Hopital's rule, right, because this is infinity over infinity, right? If you are to take derivatives of e, they will always stay as e to the x, right? Yeah, sure, the constant in front will change, right? 0.04, 0.04 squared, cubed, and so on. But e to the 0.04x would never change, no matter how many derivatives you take. But look at the bottom. The bottom is going to go x to the 7, then x to the 6, x to the 5, x to the 4, x to the 3, x to the 2, x to the 1, and then a constant. When it hits the constant, you can't apply L'Hopital's rule anymore. So now what do you have? You have infinity on top divided by some constant on the bottom. What's the answer? Has to be infinity, right? So you can't take the derivatives of the bottom until you reach 0, right? Because as soon as you reach the constant, so you have the x with the 7 factorial in front of it. No, 8 factorial in front of it. And then when you get to take that last derivative, right, you will get the number, and then it's no longer eligible for L'Hopital's. And that's that. Good question. Growth rate of functions.
My math lab was telling us to put it in terms of t and somewhat weird,
Yeah, it was weird.
obtuse way, which is why it confused me, because our notes wasn't matching that.
Maybe there's something else that is in the book that I would like to see, but it's good enough. Anything else? It will be now, since we... Growth rate of functions, L'Hopital's rule. You gotta know this for computer science, otherwise you are doomed, yes. Oh, thank you very much, I've been knitting all night. Anything else? Okay, well then that ends this one.